Welcome to submodule 1 of 3 on key concepts, which will lay the foundation for understanding optimization as a continuous engineering process. We'll explore definitions, key factors, and the workflow behind effective drilling optimization. In this session, our objectives are to build a clear understanding of drilling optimization as more than just speeding up operations. We'll see it as a continuous engineering workflow designed to deliver safer, more productive, and more cost-effective wells. Another key focus is recognizing the broad set of stakeholders who contribute. Engineers, geologists, contractors, and service providers all play vital roles in achieving optimization. We'll also identify the fundamental factors that directly influence drilling efficiency and overall performance, from equipment and procedures to control systems and supervision. The session emphasizes the importance of applying real-time data and adaptive planning, allowing us to make timely adjustments that improve results as operations progress. Finally, we'll review how continuous monitoring and structured feedback loops provide the basis for ongoing improvements in both single wells and across projects. Together, these objectives frame the foundation for how we define, plan, and execute optimization in drilling operations. Next, let's explore exactly what we mean by drilling optimization. When we talk about drilling optimization, the first question to ask is, what do we really mean by it? Let's move forward and introduce what drilling optimization is. Let's challenge ourselves with some fundamental questions. Is drilling optimization simply drilling as fast as possible? Is it about completing the operation successfully or finishing in the minimum possible time? Should it be seen through the lens of cost reduction, maximizing production, or accelerating financial break-even? The truth is that drilling optimization encompasses all of these perspectives, but none of them in isolation. Speed alone without safety and efficiency is not optimization, it's risk. Completing the operation is necessary, but not sufficient if costs spiral out of control. Achieving the minimum time possible is useful, but only if the well is fit for purpose and delivers value over its life. Optimization is about connecting these outcomes into a cohesive approach. It means designing and executing wells that meet operational, financial, and production objectives simultaneously. In other words, optimization is a workflow that integrates technical, economic, and operational priorities. With that broader definition in mind, let's refine the concept further and look at the workflow approach that truly defines drilling optimization. Ultimately, drilling optimization is best defined as a workflow process, a continuous engineering strategy that ensures every wellbore is fit for purpose, more productive, and cost-effective. This isn't a one-off effort. It's an ongoing process that must span all stages of well construction, from design to execution, control, and review. The essential point is that optimization requires a structured, repeatable workflow. Every design decision must be tested against operational realities. Every execution step should be monitored in real time. Every control loop must be tuned to achieve efficiency without compromising safety. And importantly, feedback must continuously cycle back into the design so that lessons learned today improve tomorrow's wells. This approach provides continuous improvement, not just for one project, but across the life of multiple wells. It is how we transform drilling from a task-by-task process into a true engineering system. Having defined optimization as a workflow, let's now turn to the people involved, because optimization depends on far more than just the drilling team. Drilling optimization is not the responsibility of a single discipline or a single team. It is a collective effort, requiring input from every group involved in the well construction process. This includes well engineers who design the technical program, reservoir engineers who define the production objectives, and geologists who provide critical formation knowledge to steer drilling decisions. It also extends to the drilling contractor who operates the rig, and to logistics teams who ensure that equipment and supplies are available at the right time. On top of this, every service provider, whether directional drilling, mud systems, logging, or completions, plays a vital role in ensuring that the workflow is optimized. The message is clear. Drilling optimization is a team sport. Success relies on communication, alignment, and shared ownership of objectives. No single stakeholder can optimize in isolation. True optimization happens only when all parties work together. Now that we've defined who is involved, let's look at how their work fits into the standard drilling cycle workflow process. When we talk about the standard drilling cycle, the process begins with design. Here, we define the well objectives, construct the well path, select casing and bit programs, and identify risks. The design integrates subsurface data, offset well performance, and mechanical earth models to build a safe, cost-effective plan. Next is program. This is where the engineering design is translated into a detailed drilling program, including operational procedures, equipment requirements, contingency planning, and HSE protocols. This document becomes the instruction manual for the rig site. The third stage is execute. This involves drilling the well as per the program, monitoring drilling parameters, managing hole cleaning, bit runs, and BHA performance, while ensuring safety and operational efficiency. Real-time data is essential to make proactive decisions. Once execution is complete, we move to report. Daily drilling reports, end-of-well reports, and lessons learned are documented to capture performance metrics and highlight deviations. The fifth step is control. Here we measure performance against KPIs such as NPT, cost per foot, and safety performance, allowing us to identify improvement areas. Finally, review. The campaign is critically evaluated, feeding lessons back into future designs. This closes the loop and ensures continuous improvement. Now we focus on the objectives and goals of the standard drilling and well construction process. The primary measure of success is the safe and efficient completion of the well. But beyond that, optimization means continually improving how we construct wells. Improvements can occur on a well-to-well basis, where lessons learned from one operation are immediately applied to the next. They can also be made at the project-to-project level, where knowledge is transferred across entire campaigns. Finally, we must also recognize task-level optimization, where every operation, whether it's tripping pipe, cementing, or running casing, is analyzed for efficiency and improved accordingly. The goal is to embed continuous improvement at every layer, ensuring we not only finish wells successfully, but also push performance standards higher with each project. This approach moves us from simply completing wells to building smarter, safer, and more efficient well construction systems. Next, we'll look at the fundamental factors that drive process optimization and allow these improvements to happen. Here we break down the fundamental factors that underpin process optimization in drilling. The first is equipment optimization. This means ensuring the rig and downhole tools are always being used to their full technical advantage, not underutilized or run inefficiently. Second, operating procedures play a huge role. Even with identical equipment, procedures can vary widely between rigs, crews, or companies. Standardization and automation can help reduce variability and improve repeatability. Next is control optimization. In a typical processing plant, such as a chemical plant or oil refinery, there are hundreds or even thousands of control loops. Each control loop is responsible for controlling one part of the process, such as maintaining a temperature, level, or flow. If the control loop is not properly designed and tuned, the process runs below its optimum. The process will be more expensive to operate and equipment will wear out prematurely. For each control loop to run optimally, identification of sensor, valve, and tuning problems is important. It has been well documented that over 35% of control loops typically have problems. The same holds true in well construction operations, where a typical well will suffer greater than 30% NPT. Finally, performance supervision is essential. Continuous monitoring and evaluation of drilling parameters, much like supervising a plant operation, ensures issues are detected early and improvements can be made in real time. Together, these factors form the backbone of drilling optimization, balancing technology, procedures, and oversight. Moving forward, let's examine how drilling optimization differs from the standard cycle and why that distinction matters. Let's revisit the standard drilling cycle workflow diagram we saw earlier. In that version, the process followed a familiar loop: design, program, execute, report, control, and review. The key addition in drilling optimization is the concept of continuous review, shown as an embedded element rather than a discrete step. Traditional workflows treat review as something that happens at the end of a well or a project. Optimization makes review ongoing. It's built into every stage of the cycle. Data from execution doesn't just flow into a final report, it feeds forward immediately into design and planning. That's what makes the well-planned living continuous review, means risks can be identified and addressed earlier, and performance gaps corrected in real time rather than after the fact. It transforms optimization into a dynamic, adaptive process, constantly evolving with the operation. Next, we'll expand on how communication, teamwork, and continuous improvement bring this living workflow to life. So, where does the drilling optimization workflow differ from standard workflows? The focus of the workflow is process, not task. Commonly, the process itself is risk management based. Though other process bases for drilling optimization do occur, they remain process focused. Knowledge management is the ability to transfer knowledge and skill from people to processes and systems. This must include methodologies of capturing knowledge, accessing knowledge, and being able to forecast the next stage in the process based on the knowledge. This builds into the continuous review, continuous design or redesign, by applying the process of monitoring real-time data with forward-modeled data, a greater understanding of when and how the process is diverging from the design can be identified for application of the design contingency at the correct time, not after the event. Let's take a moment to watch a video on digital drilling and how software can improve process efficiency in the design process.
SLB is transforming the well construction lifecycle from planning to execution, utilizing collaboration and automation, whilst integrating the untapped power of data and AI to create a seamless loop between town and rig, making every well better than the last. That starts with our cloud-native drill plan coherent well planning and engineering solutions, proven around the world to produce superior quality drilling programs in half the time. Next, DrillOps intelligent well delivery and insight solutions provide smart automated workflows and autonomous operations to improve consistency and optimize performance. At the heart of drill plan solutions are four key principles: automation, validation, collaboration, and coherence. Its single point of data entry and collaborative environment automate repetitive tasks, reducing manual errors, while automated engineering analysis run multiple sensitivities concurrently, reflected in real-time changes across the whole system. This ensures coherency across teams and service providers, giving engineers more time to act faster and smarter, enabling optimized, cost-efficient, and more sustainable well designs. Those designs are seamlessly passed to DrillOps, where AI-driven automation and advisory applications enable intelligent execution, delivering unprecedented performance and consistency, while also significantly reducing carbon emissions. Our advisory solutions can be deployed immediately on any rig, providing drillers smart recommendations for drilling and tripping execution. Connecting rig to town, DrillOps Predictive Analytics provides real-time decision support, unifying industry-leading domain models with AI to help predict and prevent drilling events, reducing risks, and improving performance. Throughout, daily activities and lessons learned are captured to deliver a data-driven, automated record for input into future operations and planning. With SLB, you're covered from planning to operations with solutions that optimize efficiency and performance, all to make every well better than the last.
Let's take a moment to review the objectives we set out at the start of this sub-module. First, we aim to understand drilling optimization as a continuous engineering workflow. We've seen that optimization spans design, execution, control, and review, always feeding back into the next cycle. Second, we wanted to recognize the role of stakeholders in optimization. From well engineers and geologists to contractors and logistics teams, each plays a part in the integrated process. Third, we set out to identify the core factors influencing drilling efficiency and performance. We've covered equipment utilization, procedures, control systems, and supervision as the critical drivers. Fourth, we looked at how to apply real-time data and adaptive planning. This is central to maintaining a living well plan and making smarter operational decisions. Finally, we focused on evaluating drilling processes through monitoring and feedback, ensuring lessons are learned and applied. Together, these objectives frame optimization as a cycle of continuous improvement. That concludes this submodule 1 of 3 on drilling optimization key concepts. We've explored the objectives, workflow differences, and the continuous improvement mindset required for success. Please now proceed to the quiz to reinforce your understanding of the material. Thank you for your attention and engagement throughout this session.